Good morning, all of you. In this session, I am going to explain about design of protective type flange coupling. In this class, I will explain how to design a protective type flange coupling. So this is the example for a protective type of flange coupling. Here you can observe the assembling of protective type flange. These two are the flanges. These two are the shafts. This one is a sunk key. These are the hexagonal bolts. These are also hexagonal nuts. Okay, this is the complete assemble of a protective type flange coupling. In this class, I will explain how to design this flange coupling. These are the important conversions for problems. 1 megapascal, 1 gigapascal, 1 pascal. These all are important for solving the problems. 1 pascal equal to 1 Newton per meter square. Okay, 1 pascal equal to 1 Newton per meter square. 1 megapascal equal to 1 mega equal to 10 power 6 and pascal equal to Newton per meter square. So 1 megapascal equal to 10 power 6 Newton per meter square. In similar way, 1 megapascal equal to 1 Newton per mm square. Okay, 1 megapascal also equal to 1 Newton per mm square. Okay, 1 gigapascal equal to 1 giga equal to 10 power 9, 1 pascal equal to Newton per meter square. Okay, so 10 power 9 Newton per meter square equal to 1 gigapascal. In similar way, 1 gigapascal also equal to 10 power 3 Newton per mm square. Okay, now these are important formulas for design of hollow shaft and solid shafts. Yeah, this one is the cross-sectional view of a solid shaft, and this one is the cross-section of a hollow shaft. Here, small d is the outer diameter of the solid shaft. Here, this one, small d is the inner diameter of the hollow shaft, and capital D is the outer diameter of the hollow shaft. Okay. Here, capital K is the diameters ratio of a hollow shaft. Okay. K equal to inner diameter divided by outside diameter. Okay, it is very important for solving the design of hub. Here, already we know that power transmitted by any shaft, power transmitted by solid shaft or hollow shaft, power P equal to torque transmitted by the shaft into angular velocity of the shaft. Okay, omega is the angular velocity. Omega equal to 2 pi n by 60. So the power transmitted by the shaft, power P equal to torque into 2 pi n by 60. From this equation, you can get the value of torque transmitted by the solid shaft and hollow shaft. Okay, this formula is same for solid and hollow shaft. Torque T equal to 60 into P by 2 pi n. It is very important for determining the mean torque value. Okay, after getting the mean torque value, we have to substitute this value in this equation. Torque T equal to pi dq by 16 into tau. Okay, this formula is used for design of solid shaft. Okay, after substituting the value of torque T in this equation, you can get the value of a suitable diameter of the solid shaft. Okay, in similar way, you have to substitute the value of torque, mean torque in this equation. You can get the value of outer diameter or inner diameter of the hollow shaft. Okay. Here tau is the shear stress induced in the shaft material. Okay. Now this is the formula used for design of shaft on the basis of rigidity or stiffness. Okay. Torque transmitted by the solid or hollow shaft equal to polar moment of inertia into shear modulus into angle of twist in radius divided by length of the shaft. Okay. Here J equal to polar moment of inertia. For solid shaft, J equal to pi to the power 4 by 32. In similar way, for hollow shafts, J equal to pi to the power 4 by 32 into 1 minus K power 4. Here K equal to D by D, small d by capital D, inner diameter by outer diameter. Okay. So these all are important formulas for design of solid and hollow shafts. Now these are the formulas for used for design of sunk case. Already we know the formula for power and torque. Okay. After getting the power, after getting the mean torque, you have to use these formulas. Here L is the length of the key. The length of the key is equal to the length of the hub. Okay. That value nearly equal to 1.5 times the diameter of the shaft. Okay. Length of the key equal to length of the hub. Here width of the key equal to W equal to diameter by 4. Here from this diagram you can observe from here to here, this one is width of the key, and from here to here, this one is thickness of the key, and from here to here, this one is length of the shaft, length of the key. Okay, so the width of the key is nearly equal to the diameter 1 by 4, diameter by 4, and thickness of the key T equal to diameter by 6. Now you have to check these values. For that purpose, you have to consider shearing strength of the key. This is the formula for shearing strength of the key. Torque T equal to length of the key into width of the key into shear stress induced in the key material into radius of the shaft. Okay. Now you have to substitute the value of mean torque, length of the key, width of the key, and diameter of the shaft. After substituting these values, you can get the value of shear stress induced in the key material. Okay. In second case, you have to consider crushing strength of the key. Okay, this is the formula for crushing strength of the key. Here also you have to substitute the value of mean torque, length of the key, and thickness of the key, and the diameter of the shaft. After substituting these values, you can get the value of crushing stress. Sigma C is the crushing stress induced in the key material. Okay. Now, this is the cross-sectional view of a protected, unprotected type of flange coupling. These are the important dimensions. Here, small d is the diameter of the solid shaft, and also small d is equal to the inner diameter of the hub. Okay, this is the hub. So inner diameter also equal to diameter of the shaft, and outer diameter of the hub equal to 2 times the diameter of the shaft. Capital D equal to 2d is the outer diameter of the hub. Okay, and here D1 equal to 3d is the pitch circle diameter of the bolt. Okay, and D2 equal to 4d is the outside diameter of the flange. And here L equal to 1.5d is the width of the or length of the hub. L equal to 1.5d is the length of the hub. TF is the thickness of the flange. Okay, D1 or DB is the diameter of the bolt. Here tau S, tau B, tau K are the shear stresses induced in the shaft material, bolt material, and key material. Whereas tau C is the shear stress induced in the flange material, that is cast iron material. Sigma C is the compressive stress or crushing stress induced in the bolt and key material. Here N is the number of bolts used for join the two flanges. This is the standard table. From this table, you have to choose the number of bolts required. The number of bolts depends upon the diameter of the solid shaft. Okay. Here there are 5 steps for design of protector type and unprotector type of flange coupling. Okay, there are 5 steps. In first step, you have to design a suitable size of the solid shaft. Okay, in first step, you have to design a suitable size of a solid shaft. Here, already we know that power transmitted by the shaft, solid or hollow shaft, power P equal to torque into angular velocity. Okay. Here from this equation, the torque value, mean torque equal to 60 into P by 2 pi n, omega equal to 2 pi n by 60. Okay. From this equation, you have to find the value of mean torque. Okay. After getting the mean torque, you have to use torque transmitted by the solid shaft formula. Okay, this is the formula for torque transmitted by the solid shaft only. Okay, torque equal to pi d cube by 16 into tau. Okay, from this equation, you can get the value of diameter of the solid shaft. Okay, in first step, you have to determine the suitable size of a solid shaft. Okay, in second step, you have to design a required sunk key. So this is the width of the sunk key, width W equal d by 4, and thickness of the sunk key equal d by 6. Length of the key are here for protector type and unprotector type flanges. You have to consider length of the key in each shaft is equal to the length of the hub. That value equal to 1.5d. Okay, length of the hub is equal to 1.5d. Now, for design of sunk case, you have to consider shearing strength and crushing strength. From these two values, you can get the value of shear stress and the compressive stress induced in the key materials. In third step, you have to design a hub of a flange coupling. Here, tau c is the permissible shear stress induced in the cast iron material. Outer diameter of the hub equal to 2 times the diameter of the shaft. Now, for design of hub, you have to consider a hollow shaft. Okay, so you have to treat this hub as a hollow shaft. This is the formula for torque transmitted by a hollow shaft. Okay, in this equation, you have to substitute the value of mean torque T and diameter, the outer diameter of the hub and diameter ratio. Diameter ratio is K equal to inner diameter by outer diameter. Okay, after substituting these values, you can get the value of tau c, shear stress induced in the cast iron material. Okay, in fourth step, you have to design a flange. Here, let TF is the thickness of the flange. That value equal to 0.5 times the half of the diameter. Okay, 0.5 T. Let outer diameter of the hub equal to 2 times the diameter of the shaft. Now, sigma c is the shear stress induced in the cast iron material. This is the formula for torque transmitted by the flange. Okay, torque equal to pi by 2 into d square into tau c into TF. Okay, here capital D is the outer diameter of the hub, and TF is the TF is the thickness of flange. Now T is the mean torque or maximum torque. You have to substitute these three values. After substituting these three values, you can get the value of tau c, shear stress induced in the cast iron material. Okay, you have to check this induced shear stress with the permissible shear stress. Okay, in last step, you have to design a core diameter of a bolt. Okay, in last step, we have to design a suitable size of bolt. Here, this is the formula for torque transmitted by the bolts. Torque equal to pi by 4 dB square into tau b into n into d1 by 2. Here, d1 is the pitch circle diameter of the bolts. d1 equal to 3 times the diameter of the shaft. Okay. Here, db is the core diameter of the bolt, and tau b is the shear stress induced in the bolt material. Okay. From this equation, you have to determine the suitable size of a bolt diameter dB. Okay. So these all are the steps for design of protective type and unprotective type flange coupling. You have to use these 5 steps for design of any flange coupling. Okay. Now this is the given question. Design a cast iron protective type flange coupling to transmit 15 kilowatts power at 900 RPM speed from an electric motor to a compressor. The maximum torque is 35 times greater than the mean torque. Okay, 35% greater than the mean torque. The following permissible stresses may be used. That is shear stress. Shear stress induced in the shaft material, bolt material, and key material is 40 megapascal. That means tau, tau S, tau B, and tau K equal 40 megapascal. Crushing stress induced in the bolt and key material is sigma C equal to 80 megapascal, and shear stress induced in the cast iron material, that is flange material. For flange material, tau C equal to 10 megapascal. Draw a neat sketch of the flange coupling. Okay. So this is the diagram of a flange coupling. First, you have to draw a flange coupling diagram. In this diagram, you can get the value of outer diameter of the hub and pitch circle diameter of the bolt and outside diameter of the flange. Okay. First of all, you have to identify the given values. From given question, the power transmitted by the solid shaft is 15 kilowatts. Here you can observe the power transmitted by the solid shaft equal 15 kilowatts. Okay, 1 kilo equal to 1000. So 15,000 watts. 1 watt equal to Newton meter per second. Okay, so the power is in meters. Now the speed of the shaft is 900 rpm. N equal to 900 rpm. And here the shear stress induced in the shaft and key material is 40 megapascal. Okay, tau S and tau K, tau B equal to 40 megapascal. 1 megapascal equal 1 Newton per mm square. Okay. Now the shear stress induced in the cast iron material, that is the flange material, is 10 megapascal. So tau C equal to 10 megapascal. And here the crushing stress for bolt and key material is sigma C. Sigma C equal to 80 megapascal. 1 megapascal equal 1 Newton per mm square. Now here the tensile stress induced in the bolt material is 80 megapascal. Okay, sigma T equal to 80 megapascal. Now you have to apply 5 steps for design of flange coupling. Here I consider step 1, that is the design of solid shaft. For design of solid shaft, you have to consider a power transmitted by the solid shaft. Here P is the power transmitted by the solid shaft and T is the torque, mean torque. Omega is the angular velocity. Omega equal to 2 pi n by 60. Okay. So already from given question, already we know the value of power and angular velocity. So here from this equation, you can get the value of mean torque transmitted by the solid shaft. Torque T equal to P by omega. Okay, P by omega equal to 60 into P by 2 pi n. Now you have to substitute the value of power and the speed of the shaft. Okay, already we know the speed of the shaft. N equal to 900 rpm and power P equal to 15,000 Newton meter per second. Okay, 15,000 watts. So from this equation, you can get the value of mean torque. Torque T equal to 159.13 Newton meter. Okay. Here the power is in Newton meter. So the torque value also in Newton meter. After getting that, you have to convert this meter into mm. 1 meter equal to 1000 mm. So 1,59,130 Newton mm. Okay, is the mean torque. After that, in our question, the maximum torque is given. The maximum torque is 35% greater than the mean torque. So you have to consider a 1.35 service factor. Okay, that means 100% mean torque plus extra 35% mean torque. 100 plus 35, 135%. 135% divided by 100 equal to 1.35. Okay, so 1.35 is the service factor. So for getting the maximum torque, you have to use this formula: maximum torque equal to service factor into mean torque. Okay, so here the service factor is 1.35 and mean torque equal to 159.13 Newton meter. Okay, so from this equation, 215 into 10 power 3 Newton mm. This is the maximum torque. So after getting the maximum torque, you have to apply the torque transmitted by the solid shaft formula. So from this formula, you can get the value of a suitable diameter of a solid shaft. Okay, maximum torque equal to pi d cube by 16 into tau. Okay, from this equation, you can get the value of diameter, small d, is the outer diameter of the solid shaft. Okay. Now you have to substitute value of tau. Tau equal 40 mega. From given data, already we know that shear stress for shaft material, tau equal 40 megapascal. So from this equation, 215,000 equal to pi d cube by 16 into 40. Okay. So suitable diameter of the shaft is 30.1 mm. Okay, d equal to 30.1 mm. This is the required diameter, but the standard size is 35 mm. Okay. The available standard size of shaft is 30, 35 mm, 40 mm. So you have to consider this standard size 35 mm. Okay, 35 mm is the suitable diameter of the shaft. In second step, you have to design a sunk key. Okay, shear stress for shaft and key material. Shear stress for shaft and key material is tau equal to 40 megapascal. And the compressive stress or crushing stress for key material is 80 megapascal. Here you can observe the crushing stress is 2 times the shearing stress. Okay. Here the crushing stress sigma c equal to 80. Shear stress is 40. That means the crushing stress is 2 times the shear stress. So you have to consider a square key. Okay. Square key. You have to consider a square key. For square case, the width and thickness both are equal. Okay. For square case, width and thickness both are equal. Already we know that width of the key equal to diameter by 4. So diameter is 35 mm. Already we got in step number 1. So diameter of the shaft d equal to 35 mm divided by 4 equal to 9 mm. That is the width. And here the thickness also same. So thickness of the key equal to 9 mm. After that, you have to calculate the length of the key. Length of the key equal to length of the hub, that value equal to 1.5d. Length of the key equal to length of the hub, 1.5d. 1.5 into 35 equal to 52.5 mm. So these all are dimensions of a square key: width, thickness, and length. Okay. Now you have to check these 3 values. Now you have to consider crushing. Sorry. Now you have to consider shearing strength. Shearing strength of the key. Okay, this is the formula for shearing strength of the key. So here T max, that is the maximum torque, length of the key, width of the key, and shear stress induced in the key material into diameter of the shaft divided by 2. Here from this equation, you have to substitute the value of maximum torque and length of the key and width of the key and the radius of the shaft. After substituting these 3 values, you can get the value of shear stress. Shear stress induced in the key material. Okay, that value equal to 26 megapascal. But from our given question, the shear stress induced in the key material, the shear stress for key material is 40. So 26 megapascal is the induced shear stress. 26 megapascal is the induced shear stress, whereas 40 megapascal is the given permissible shear stress. This induced shear stress is less than the permissible shear stress. So the design of key on the basis of shearing strength is safe. Okay. In similar way, you have to consider the crushing strength of the key. Here, this is the formula for a crushing strength of the key. In this equation, you have to substitute the value of maximum torque, length of the key, and thickness of the key, and radius of the shaft. After substituting these 3 values, you can get the value of crushing stress induced in the key material. Okay, so sigma c equal to 52 megapascal. But in our question, the sigma c equal to 80 megapascal. 80 megapascal is the given permissible stress. 52 megapascal is the induced crushing stress. So this induced crushing stress also less than the permissible given stress. So here also the given key. So the design of key on the basis of crushing strength also safe. Okay, since the induced shear and crushing stresses are less than the permissible shear stresses, therefore the design of key also safe. Okay. In third step, you have to design a suitable size of hub. So this is the cross-sectional view of a hub. So small d is the diameter of the solid shaft. that value also is equal to inner diameter of the hub. Capital D is the outside diameter of the hub. Capital D equal to 2 times the diameter of the shaft. So capital D equal to 2D. Okay, capital D equal to 2 into small d. Here tau C is the shear stress induced in the cast iron material. Okay, this is a flange material. So here we are using cast iron material for flange. So sigma C is the shear stress induced in the cast iron material. Now here capital D equal to 2 times the diameter of the shaft. That value equal to 70 mm. Now this is the formula for torque transmitted by the hollow shaft. Okay, the torque transmitted by the hollow shaft T equal to 5 by 16 into tau C into d cube into 1 minus k power 4. Here k is the diameter ratio, inner diameter by outer diameter. Okay, that value is equal to 0.5. Okay, here inner diameter is 35 mm and outside diameter is 70 mm. So k equal to 0.5, and here capital D equal to 70 mm and k equal to 0.5, and T max. This one is a T max, maximum torque. Okay, here you have to substitute the value of maximum torque, capital D and K. After substituting these three values, you can get the value of shear stress induced in the coupling material, tau C. Okay, so from this equation, the shear stress induced in the cast iron material is 3.4, but this is the given permissible shear stress. This is the induced shear stress. This induced shear stress is less than the permissible given stress. So the design of hub is safe. Okay. In fourth step, you have to design a flange, protective type flange. So for that purpose, you have to consider thickness of the flange, TF equal to 0.5 into D. Okay, this is the flange. Okay, so 0.5 D is the thickness of the flange. And here capital D is the outer diameter of the hub. Here capital D equal to outer diameter of the hub. And tau C is the shear stress induced in the flange material and hub material. This is the formula for torque transmitted by the flange. Now here you have to substitute the value of maximum torque and the diameter of the hub and thickness of the flange. After substituting these three values, you can get the value of shear stress induced in the flange material. Okay, from this equation, tau C equal to 1.6 Newton per mm square. But the given permissible shear stress is 10. Okay, this is the induced shear stress. This induced shear stress is less than the permissible shear stress. So the design of flange also safe. Okay. Now consider protective flange. TP is the thickness of the protective flange. That value equal to 0.25 into diameter of the shaft. Okay. Now this is the last step. In the last step, you have to design a suitable size of bolts. Okay, these are the bolts. Here you can observe this is the pitch circle of the bolt. That pitch circle diameter of the bolt equal to 3D. Okay, 3D is the pitch circle diameter of the bolt. Let DB is the core diameter of the bolts. Here, this is the bolt. So the diameter of the bolt is DB. And here the number of bolts required for join these two flanges is 3. N equal to 3. Okay, N is equal to 3 is the number of bolts required. Shear stress in bolt material is tau B equal to 40 megapascal. This is the given value. And here D1 is the pitch circle diameter of the bolt. That value equal to 3D equal to 105 mm. Now already we know that D1 equal to 3D. Here this is the formula for torque transmitted by the bolt materials. Torque transmitted by the bolts equal to maximum torque equal to 5 by 4 into dB square into tau B into N into D1 by 2. In this equation, you have to substitute the value of maximum torque and shear stress induced in the bolt material and number of bolts and pitch circle diameter of the bolt D1. Okay, after substituting these 4 values, you can get the value of bolt diameter, core diameter of the bolt. core diameter of the bolt equals 6.6 mm. Okay, this is the required size of the bolt. Okay, after getting this value, D2 is the outside diameter of the flange. That value equal to 4D. 4D equal to 140 mm. Okay. So here I completed 5 steps for design of a protective type flange coupling. Okay, this is the complete answer for this problem. Now this is another example problem. Design and draw a cast iron flange coupling for a mild steel shaft transmitting 90 kilowatts at 250 rpm. And the angle of twist is not to exceed 1 degree in a length of 20 diameters. The following permissible stresses may be used. Shear stress for the shaft key material tau equal to 40 megapascal. Shear stress for bolt tau b equal to 30 megapascal. Crushing stress for key, that is sigma c for key material equal to 70 megapascal. Shear stress for cast iron, that means tau c equal to 8 megapascal. Shear modulus, that means capital C equal to 84 gigapascal. Here, from given question, the power transmitted by the solid shaft is power P equal to 90 kilowatts. 1 kilo equal to 1000 watts. So 90,000 watts. 1 watt equal to Newton meter per second. Okay. Speed N. Here, the speed of the solid shaft N equal to 250 rpm. Here, the angle of twist is given, that is theta equal to 1 degree. Okay. And the shear stress for shaft material equal to 40 megapascal. Shear stress for cast iron metal tau c equal to 8 megapascal. Crushing stress for key material and bolt metal is 70 megapascal, 30 megapascal. Sigma c, sorry. Shear modulus equal to C, capital C or G equal to 84 gigapascal. Okay, 84,000 Newton per mm square. Here the angle of twist theta equal to 1 degree. 1 degree equal to, you have to convert this degrees into radians. So 1 degree equal to pi by 180 radians. Now theta equal to 0.0175 radians. Okay. Now length of the shaft L equal to 220 diameters. That means 20 times the diameter of the shaft. Okay, length of the shaft equal to 20 into D. In first step, you have to design a suitable size of solid shaft. Okay, so torque equal to 60 P by 2 pi n. From this equation, you can get the value of mean torque. After getting the mean torque, you have to use this formula for determine the diameter of the shaft. In case 1, you have to design a shaft on the basis of strength. Torque equal to pi d cube by 16 into tau. From this equation, you can get the value of diameter of the shaft. Okay, 76 mm. Okay, this is the required diameter of the shaft on the basis of strength. But in our question, we have angle of twist and shear modulus and length of the shaft. So you have to design a shaft on the basis of rigidity or stiffness. Here from given question, capital C, shear modulus or modulus of rigidity equal to 84 gigapascal, that value equal to 84,000 Newton per mm square, and the angle of twist equal to 1 degree equal to 0.0175 radians. 1 degree equal to pi by 180 radians. Okay. And length of the shaft equal to 20 times the diameter of the shaft. Now you have to substitute these 3 values in this equation. Already we know the value of torque. Okay, torque T equal to 34 lakhs 40,000. So you have to substitute this value in this equation. And here J for solid shaft equal pi d power 4 by 32. Okay. Now substitute these values in this equation. From this equation, you can observe small d is the unknown value. Okay, small d is the diameter of the solid shaft. So you can get the value of small d, diameter d equal to 78 mm. From these 2 values, you can observe this is the diameter of the shaft on the base of strength. This one also diameter of the solid shaft on the base of rigidity or stiffness. Taking larger of these 2 values, here the larger value is 78 mm. So the required or suitable diameter of the shaft is 78 mm, but the standard size is 80 mm. Okay, the standard size of shaft is 80 mm. So you have to consider 80 mm as required shaft diameter. Okay. In step number 2, you have to design a suitable size of key. Here, the crushing stress for key material is 70 and the shear stress is 40. So here, this crushing stress is not equal to 2 times the shear stress. So you have to consider rectangular key. Width of the key equal to 20 mm, thickness of the key equal to 14 mm, and here this one is the length of the key equal to length of the hub. Now substitute the values in this equation. You can get the value of shear stress induced in the key material. Okay, shear stress induced in the key material equal to okay, from this equation you can get the value of crushing stress induced in the key material. Okay. In third step, we have to design a suitable size of hub. Already we know the steps. Okay, capital D is the outside diameter of the hub. That value equal to 2 times the diameter of the shaft. That is 160 mm. Now this is the formula for torque transmitted by the hollow shaft. You have to substitute these values in this equation. You can get the value of shear stress induced in the hub material. That is cast iron material. Tau C equal to 4.56 mm, 56 Newton per mm square. This value is less than the permissible stress, 8 megapascal. Okay, so the design of hub is safe. In fourth step, we have to design a suitable size of flange. Okay, this one is the flange. Okay, TF is the thickness of the flange. That value equal 40 mm, and diameter of the hub equal to 160 mm. Okay, this is the formula for torque transmitted by the flange. Now you have to substitute the value of maximum torque and hub diameter and thickness of the flange. Okay, here from this equation you can get the value of shear stress induced in the cast iron material. This one value is 2.14 Newton per mm square. This value is less than the given permissible value. So the design of flange also safe. Okay, this one is induced shear stress. This one is given permissible stress. The induced shear stress is less than the permissible shear stress. So the design of hub or design of flange are safe. In last step, we have to design a suitable size of flange bolts. Already we know the formula for flange bolts. Here the diameter of the shaft is 80 mm. That means the diameter is more than 40 mm. So you have to consider 4 number of bolts equal to 4. Okay. Now you have to use this formula for determine the size of the bolt. dB is the core diameter of the bolt. Now you have to substitute the value of maximum torque and bolt shear stress in the bolt material and number of bolts and the pitch circle diameter of the bolt. D1 is the pitch circle diameter of the bolt. D1 equal to 3D. Okay. From this equation, you can get the value of core diameter of the core diameter of the bolt. That value equal to 17.4 mm. Okay, this is the required size of the bolt. Okay. So this is the complete answer for this problem. In next class, I will explain design procedure of a flexible flange coupling.